My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Adda, and School of Astrophysics and Astronomy, and YouTube channel, Pretam Kumar. I'd like to welcome you all to our International Physics webinar. So, good evening to all here in Bangladesh, and a very good afternoon to all those who are watching this from this webinar live from UK. So, hope you are well and safe from Corona pandemic. So, as we all know that we are staying in a corona pandemic situation, so uh, uh, we have to maintain our health rule. So we would like to discuss about the department of physics, Pabna University of Science and Technology, and the department of physics and astronomy, Professor Department of Physics and Astronomy, Professor of Gravitational Waves and Dark Matter Physics, the University of Sheffield, UK. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. And we have successfully completed our 158th international physics webinar. Today it's our 159th. So we are trying to adjust with this new normal situation. So as we cannot continue our normal academic program inside the campus, we have to start our online program. So today I would like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, the University of Sheffield, UK. And we have with us here today Dr. Edward Dow, Professor, Department of Physics and Astronomy, and Professor of Gravitational Waves and Dark Matter Physics, the University of Sheffield, UK. And he has already connected with us, so I'd like to welcome our speaker. So, sir, good evening and good afternoon to your part. Thanks for accepting the invitation, sir. So, we'd like to say thanks on the behalf of the Department of Physics, Pabna University.
You're quite welcome. I'm very happy to be here with you. Is it time for me to start speaking now? Everything's gone a bit quiet. Looks to me like things are frozen. It's fine, I'll just wait. Unless you tell me to go, then I will go.
Sorry, I have disconnected due to the electricity. So, before going to our speaker, I'd like to introduce our speaker with all of you. And then our speaker will deliver his speech, and at the end we have a discussion session, and you can ask question by commenting also. So I think you have already come to know the title of this today's international physics webinar. Our title is the Searching for Dark Matter Axions, and our speaker is Dr. Edward Dow, Professor, Department of Physics and Astronomy, Professor of Gravitational Waves and Dark Matter Physics, the University of Sheffield, UK. And we can see his record of experiment and other research. So experimentally, he is currently working as a ADMX, the Axion Dark Matter experiment, and LIGO, the Gravitational Wave Detector. He is currently the principal investigator of the quantum sensor for the Hidden Sector project, a funded research program to build a world-class hidden sector experiment in the United Kingdom. He has visited India in connection with the LIGO India project and has given talk at the National Physical Laboratory in New Delhi and IUCAA Institute in Pune. So we can see his educational and professional background. So he completed his bachelor degree in physics from the University of Oxford and his PhD from MIT, and he started his postdoc at MIT, and then he did his postdoc again at the University of Louisiana State University, and then he joined as a reader in the Gravitational Wave and Dark Matter Physics, University of Sheffield, and now he's currently working as a professor of the same university, University of Sheffield. So professional activities: principal investigator of the University of Sheffield Web Research Group, principal investigator of the UK Quantum Sensor for Hidden Sector Collaboration, member of the ADMX Axion Dark Matter Experiment Collaboration, and this is his research interest: dark matter sources, gravitational radiation, axions, signal processing, dynamic wave tracking, and motor control. And this is his feature publication. So thanks for all of your patience. Now it's time to go to our speaker. So sorry for this electricity disturbance. So thanks again, sir.
It's fine. It's no problem. I'm very happy to be speaking. Somebody should tell me if I speak too fast, because it's my habit sometimes to speak a bit quickly. And there's this nice poster which Dr. Das made, so I thought I'd make that my first slide because he put a lot of work into it. So my title is Searching for Dark Matter Axions. Now, just as a bit of history from my point of view, Axion searches started when I was really very young. I was about 22 years old and I just got to MIT, and I decided that I didn't really want to be an accelerator particle physicist anymore. My ambition up to that point had been to work on accelerators, but after doing some work experience, I decided it wasn't really for me. And there was a new professor in my group, a man called Leslie Rosenberg, who was the principal investigator of the experiment, which is now called ADMX, the Axion Dark Matter Experiment. At the time, it didn't really have a name because there weren't very many Axion experiments, and so you didn't need to have a name. You were just that bunch of people looking for axions. So I did my PhD on that experiment, and then I decided to change fields because there weren't any jobs in axions. It was a very unpopular field at the time. So I went to work on gravitational waves, and as you know, that turned out to be a very good thing, and gravitational waves have now been detected by LIGO. And so that was all very nice, and I was part of that, and it was a privilege to be part of that experiment. And now that that has sort of happened, I've decided with some encouragement to go back into axion searches, because axions in the meantime have become much more well motivated and popular with physicists, and so now there's a much greater amount of interest in that area, which is one of the reasons I've got back into it. So you may or may not, I don't know, have heard of the galactic dark matter problem. So I apologize for those of you who know a lot more about physics, and this is the wrong level, but of course I don't know who's listening, so I have to pitch my talk at a level that I have guessed with no input data really. And so here's what the galactic dark matter problem is in a nutshell. When you look at a spiral galaxy, and this one is M33, and of course we also reside in a spiral galaxy, the shape of the galaxy and the spiral arms sort of immediately tell you that it must be rotating. And the rotation of the galaxy is governed rather like a solar system by laws of gravitation. And in fact, Newton's law of gravitation is perfectly adequate to model the dynamics of the rotating galaxy. And the way you then go and compare your predictions from Newton's laws with how the galaxy should rotate, with actually measuring how it does rotate, is you look at the redshift, the frequency shift of light from spectral lines of hydrogen gas. And the advantage of doing it that way is that the hydrogen gas cloud around the galaxy extends further out than the visible stellar cloud that you can see with an optical telescope. So you measure the Doppler shift of those spectral lines, the change in frequency divided by the frequency the lines would have in the lab. And then you infer from that how fast the gas is rotating around the galactic center. And the prediction from very simple theory that you can do yourself on one piece of paper is that the velocity should fall with 1 over the square root of the distance from the center of the galaxy, at least outside the visible core. That should be the behavior. What you observe in reality is that, in fact, the velocity of rotation doesn't decrease as the square root of the radius. For many galaxies, it is actually a constant. For this galaxy, it's even going up a little bit, but the normal state of play, the normal thing, is to see the velocity of rotation remain flat as far out as you can measure the hydrogen. Now, there's various ideas as to what could explain this behavior. One idea, for example, is that Newton's laws of gravity are wrong at very large, I should say, at very small values of acceleration. And there's a theory called MOND, or modified Newtonian dynamics, which attempts to modify Newton's laws to match the data. And in fact, it's quite successful at doing that for the data that we have. However, we don't really want to have to modify Newton's laws of gravity, because then we'd have to modify all of physics. And so that's a big step to take. So the idea that most people have latched onto is instead of that Newton's gravity is actually correct. And what we're seeing is that the galaxy is much larger than you think it is. So in other words, there's other material in the galaxy which is not contributing to the observed galaxy. It's not visible through telescopes. Neither does it cast a shadow. It doesn't make any absorption of light coming from behind the galaxy. It's effectively invisible matter. That should be what it's called. It should be called the galactic invisible matter problem. Instead, it's called the galactic dark matter problem, and the material that we don't understand is called dark matter. And so so basically searches for particles like axions are searching for the dark matter in our galaxy by building experiments designed to detect it directly, assuming that the dark matter is spread out evenly enough that there's dark matter passing through the Earth and through us all the time. Now, of course, that's a big assumption, but you have to start somewhere. So the dark matter is actually probably only about 20 or 25% of the matter in the universe as a whole. The universe as a whole has its own dark matter problem. I call it the cosmic dark matter problem. And it's different because most of the stuff in the universe is currently thought to be this other component, which has been given the rather strange name of dark energy. It's even more mysterious than dark matter. And so if you ever think that physicists are terribly smart and they have answers to all the questions that you may ask, then this just shows you how silly we actually are, because in fact, a good deal less than 10% of the stuff in the universe is currently understood. So there's plenty more science left to do. So if you are a young person interested in becoming a physicist, don't think that you're moving into a mature field. You're not. You're moving into a very active field with a lot of work left to be done. So I know there's a lot of stuff on this slide, so I'll try and make it simple. So let me tell you about the Axion, because the Axion didn't actually start out as a dark matter candidate. The way the Axion was born is out of the physics of strong interactions. So as you know, or as you probably know, particle physicists have this model called the Standard Model of Particle Physics, which has come out of years and years and years of observing how things behave in particle beam accelerators, like the one at CERN, for example, or at Fermilab. And what they found is that basically you can break the field theory that describes most of the things in the universe, with the exception of gravity, into three pieces. There's a piece that describes nuclei, the nucleus of the atom, and how nuclei are bound together using quarks and gluons. And the mathematical name for that piece is called SU3. There's a piece that describes weak interactions and the mechanism by which particles gain mass. And that's got things like the W and Z bosons in it, and also the recently discovered Higgs boson. And that bit has the mathematical name SU2. And then there's the photons that travel from place to place and have infinite lifetime and allow us to observe the universe. And they're in a sector of the theory called U1. Now, the numbers and the lengths of the names give you an indication of how complex the bits of the theory are. So the simplest bit in many ways is the photon bit. And then the next simplest bit is the W and the Z and the Higgs bit, the SU2 bit. But even that bit isn't that simple. It turns out that it violates a symmetry called CP. And that's been discovered by looking in accelerators at particular particles called mesons, in particular the K mesons, and discovering that the way they decay is CP violating. So when we get to the most complicated bit at all, which is the SU3 bit, which describes quarks and nuclei, we might expect that that bit would violate CP as well. And rather surprisingly, it doesn't. It turns out that the SU3 part of our standard model conserves the CP symmetry. And the evidence for that is in the electric dipole moment of a simple neutron. So if you take a neutron and you try to figure out what its electric dipole moment would be, then you might do it by just writing down the radius of the neutron, which is about a femtometer, 10 to the minus 13 centimeters, and then writing down the charges that are rattling around inside a neutron, and they're quarks, which have charges of order the electron charge. So you might expect the electric dipole moment of the neutron to be 10 to the minus 13 of the electron charge times a centimeter. Now, when people go and measure it, they discover that the upper limits they get constrain it to be less than 10 to the minus 26 centimeters. Now, that's a 13 order of magnitude discrepancy. So that tells you that for some theoretical reason, the SU3 part of the standard model is precisely CP conserving. And we don't understand this. And the not understanding bit is got a name. It's called the strong CP problem. Now, as you might be expecting from the title of my talk, Axions in fact solve the strong CP problem, and the way they do it is quite complicated, and I don't think I should try and explain it in great detail. So I've drawn a picture which explains it a little bit. So you have to imagine that the vacuum, the thing that's the supposed nothingness all around it, has an interesting structure, and that structure can be modeled as a potential V. And the shape of the potential is the same as the shape of the bottom of a wine bottle or a Mexican hat. It's got a ring of minima. Now, this wine bottle in this potential is actually slightly tipped up to one side by these effects called axial anomalies, so that there is a preferred state at a particular value of this parameter theta bar. Now, the theta bar parameter also turns out to be the coefficient of the CP violating bits of our model. So that when you have this potential with these perturbations, and the perturbations are induced by invoking the existence of a new particle called the axion, then these CP violating effects go away. So the appearance of the axion in the theory actually makes the CP violation, which you measure not to be there, actually disappear in the theory as well. So it makes everything work. So axions, once you've introduced them, you start to ask questions. Well, if these particles exist, what are they like? How do they behave? Well, the first thing is they have a coupling to two fermions. So the thing on the bottom left, where you have an A and two FFs coupled together at a point, those fermions could be electrons, they could be quarks, for example, in some theories. There's a coupling. Now, if you use that coupling, you can look at you can make a slightly more complicated coupling. That's the one on the right with the box around it. That's an axion coupled to a fermion loop, and then the other vertices of the triangle are connected to photons. So by this mechanism, an axion can couple to two photons. And the strength of that coupling, how often it happens, is proportional to the axion mass. So if your axions are heavier, then you get a stronger coupling to photons. So that's the axion. It's interesting. It's an example of an axial anomaly that produces these things. And the characteristics of axial anomalies are that the strengths of the couplings of your particles scale with their masses. Now, we don't know that the axion exists, so we certainly don't know its mass. So we don't know how strongly it is coupled. So how do you look for axions? Well, this is a cartoon drawing. And the reason this guy at the top right has got his head on this slide is because that's Pierre Zakhevi. And he was, I think he probably, along with a man called Dave Tanner, they're both my friends, sort of invented the Axion Detector, which is commonly used. And basically the way it works, it's not a particle accelerator, and it's not a WIMP detector, so it doesn't involve single collisions of particles. What it's doing is trying to sort of tune in to a signal from axions converting into photons. The way it does it is you have a cavity, which is basically an empty metal box. Well, it's almost empty. There's one thing it's got in it is a metal post. And you move the metal post around, and as you move it, it changes the frequencies of the cavity modes. Now, you also have a circuit which is analogous to, it's not the same thing as, but it's analogous to an AM radio, an ordinary radio receiver, with its antenna dipped into the cavity. So as you move the tuning rod and change the frequency, you also tune the radio to change its sensitive frequency to match the mode with the frequency that it has with the rod in its current position. And then you take the output of the radio, you can sort of imagine that being the headphone socket, you plug it into a digitizer and you collect data. So you move the rod, you tune the radio, collect some data, then you move the rod again, and so on. Now, one thing that's important is that the axions is got some properties which allow us to design this detector, allow us to know what conditions axions from our dark matter halo will convert into photons under. And the main condition is that this resonant cavity has to be immersed in a strong magnetic field. So you need a big magnet. And without the magnet, you don't get a signal. That's very important because if you detect a signal, you don't know whether it's signal from axions or noise from your electronics or from some other source. But if you change the strength of the magnetic field and the signal strength doesn't change, then you know its background. If the signal strength changes in the way predicted by the theory, then you have a very strong indicator that it's a signal. So the nice thing about this detector is it gives you the ability not only to detect the axions if they're there, but also to study them, to make sure that you've actually seen something real. And that's an absolutely critical advantage. So essentially, I don't think I want to flip this slide. It's the same thing again, so I'm just going to skip it. This is a picture of the experiment. What you can see on the left is a sort of a shimmering metal cylinder. It's about 4 meters high. It's actually being pulled out of a hole in the ground using a crane. And the people in the background, that's Gray Ribka. The guy behind, I think the person behind the experiment, I'm not actually sure who that is. The person on the right is a guy called Nick Dew. And that's on the right at the back with his hands on the ropes. I think that's a guy called Gianpaolo Carosi. And so the reason it's shimmering and covered in smoke is it's just been pulled out of the bore of a very large magnet, which is in the ground. And its temperature when it's in the ground at the outer envelope of this is about 77 Kelvin. So the whole thing is at liquid nitrogen temperature, and that's why it's got frost pouring off it. That's water vapor from the air condensing close to the cold surface. On the right, you can see the inside of one of our cavities with the 2 tuning rods in it, actually. And at the bottom is a critical technology element of these experiments, which is very, very low noise superconducting electronics, because the signal strength you expect from axions is about a yoctowatt. Now, you might never have used yocto. Yocto means 10 to the minus 22. So 10 to the minus 22 watts of signal power. So that's a very small amount of signal. So in order to not to be completely buried in electronics noise, we require our amplifiers to be essentially the lowest noise amplifiers in the world at this frequency range. And this is an example of such an amplifier. It's based on a superconducting quantum interference device, and it was made by Ifran Siddiqui's group at the University of Berkeley in the United States. And the quantum sensing group that I'm running in the UK is going to try and produce its own ultra low noise amplifiers using similar technologies here in the UK. And that's one of the reasons we are funded to work in the UK now. Okay, so what you do is you keep tuning the cavity and tuning the radio, and you collect data at each of the positions of the tuning rod. And then you make power spectra out of that data using a Fourier transform. And then what you expect to see is excesses above background in the spectra, but the individual spectra on their own, only for the very strong signals do you actually see a peak in an individual spectrum. What you usually see is when you combine many spectra, the peak will appear out of the noise. So in this plot, you can see 2 injected signals in these spectra. The ones on the right are fairly obvious, and that's because this breed of axion, called the KSVZ axion, is particularly strongly coupled. Well, it's a few yoctowatts as opposed to a fraction of a yoctowatt, so it's not huge amounts of power, big enough so you can see it in an individual spectrum. On the left, you see another model of axions called the DFS-Z axion, and those are not visible in the individual spectra, but when you add up all the spectra, you see a little peak appears in the combined data. So this plot is a sign that the ADMX experiment is sensitive to these DFS-Z axions. And the reason that's important is because it's the first experiment in the world to actually be sensitive to them. It hasn't detected any, but if they were there at these frequencies, they would have been detected. So how has ADMX done in terms of covering parameter space? So the parameter space in question are the things we don't know about axions. And we don't know that much about axions, so there's a big parameter space. So on the horizontal axis is the possible axion mass, all the way from 10 to the minus 10 electron volts up to about 10 electron volts on this scale. I have to say, by the way, that there's additional quite important details about the likelihood of different axion masses. There's a particular point called the at 10 to the minus 6 electron volts, or a micro electron volt. If axions are lighter than that, then we're talking about axions that were produced before inflation ended, if you know anything about inflationary cosmology. So if axions are at 1 micro electron volt, they were produced essentially while inflation was ending or just after it ended. And at that mass, they would close the universe, so that the universe would be dominated by axions. As the axion gets heavier, going up to 10 to the minus 4, 10 to the minus 2 electron volts, the abundance of axions, it drops cosmologically, so you'd expect there to be less axion dark matter. So the place you want to look is exactly where ADMX is looking, which is at a few micro electron volts. And if you zoom in on the vertical axis, by the way, actually that's the other thing we don't know, is the coupling of axions to photons. Now, as I said before, for axions which were invented to solve the strong CP problem, the coupling and the mass are related, and so you get these yellow stripes that relate the coupling and the masses for the different models. But if you don't particularly require your axions to solve the strong CP problem, there's a more generic type of particle called an axion-like particle that could exist anywhere in this parameter space, not just on the yellow stripes. Right, that's a zoom in of the bit that ADMX has covered. So it's gone between about 2.7 microelectron volts and about 3.3. And the blue in the background, the blue run labeled ADMX 2010, that was the work I did my thesis on. And more recently, they've used lower noise amplifiers. So they're now covering, illuminating the spaces of mass down all the way down to the DFSZ model in the same frequency range. So that work has now actually been published. It says accepted by PRD, but this slide's a little bit old. It's all been published, this stuff. It was actually spearheaded by Chelsea Bartram, who's the postdoc I work with on this project of ADMX. So all this is great, right? Well, we've got the world's most sensitive Axion detector. It's running, it takes data, it produces results, it might detect axions. Wonderful. But there are also some drawbacks. There always are with experiments. So let me attack one part of the experiment that I think is a weak link. The first thing that I think we need to do is to stop using cavities, and I'll tell you why. The first thing is that there's a form factor which dictates how efficiently axions convert into photons in the cavity. And it is a function of which cavity mode you're using. So in practice, the only useful mode is a mode called the TM010 mode. And I'll try and show you a picture of that if I have time. The other thing is that you have to wait at each frequency for a very long time because the signal's very weak. Imagine you're tuning a radio and trying to detect a weak radio station. You'd tune very slowly, wouldn't you? And the same is true of physics analysis. You tune slowly if you're looking for a weak signal. And that slowness means that the experiment takes a very long time. So if you remember, I started working on this experiment when I was 21. I'm now 51. So the experiment's 30 years old. So it's taking a long time to cover the parameter space, and that's a weakness of the experiment. The other thing is this mechanical tuning mechanism when you move a tuning rod around inside the cavity. It sounds easy. Well, it's not easy if your experiment is 100 millikelvin, because anything you try and move at a very low temperature is you can't use any lubricant because all lubricants become concrete at that temperature and things wear out, and even getting the mechanical actuation into the vacuum system is complicated. And so it boils down that you don't really want to have a tuning mechanism, but you're stuck with it in this experimental configuration. And finally, because your frequency of your mode is in the end determined by the boundary conditions in the cavity, you're basically limited how much you can tune. And in practice, you can only tune to about plus or minus 15% of the natural frequency of the mode, and then you need to get a different cavity. And that can get very time consuming and expensive as well. So it'd be nice to get rid of the cavity somehow, but how do you do it? Well, here's an analogy I'd like to make. I don't know if anybody in Bangladesh is a fan of blues or jazz or any kind of electronic music. I don't know how many people there have electric guitars and that kind of thing. But in the West, of course, these things are very popular. I myself am a pianist. And so I've played in a lot of bands. And one thing that's alarming when you play in a rock band is if the guitarist decides to lean his guitar or her guitar against the amplifier, because that creates what's called a feedback loop. And the result is that typically a tone will start up. It gets louder and louder. And if you've got a high power amplifier, it can get very loud indeed and very painful to listen to. And it's not anybody playing the guitar that's causing this, it's feedback. So what happens is the speaker is putting out whatever the guitar plays. It generates pressure waves in the air. Now, those pressure waves can actually make the strings vibrate. When the strings vibrate, they create an electronic signal because of the pickups of the guitar. That electronic signal is boosted through probably some effects pedals and then into the amplifier, where it gets amplified and comes out to the speaker again. So you can see what's going to happen. There's a closed loop. Now, if it turns out that if that loop has a gain of more than 1 around it, so in other words, if the signal coming out of the speaker coupling into the strings makes the strings vibrate more than they were vibrating to create the signal that made the speaker go in the first place, if that's true, that's called the Nyquist stability criterion, then you will have a tone. In other words, the loop will generate an oscillation. And in other words, still, you've made a resonance. So this got me thinking that perhaps this kind of feedback could be used to make a different kind of Axion detector. Because the thing to remember is that if you have a feedback loop, any element of the feedback circuit that has a preferred frequency of vibration can determine the frequency at which you make your oscillator. It doesn't have to be the length of a string. It could be a characteristic of a circuit as well. Here's another analogy. So resonance is a very generic concept. So here's a simple example of a resonator. What this is it's two beads on a wire, and the wire's under some tension, so the vertical motions are greatly exaggerated. You have an incident wave from the left, and of course it makes the left-hand bead vibrate up and down, and that couples to the right-hand bead, and that starts vibrating up and down too, and then maybe you have some transmitted signal that goes off to the right. But the way you model this mathematically is you have a field inside between the two masses that bounces off the masses and circulates between them. And that circulating field, if you have a resonant condition created, so for example, if the gap between the masses is about n times the half wavelength of the wave, then you get a bigger amplitude between the masses than you get coming in or going out. And that's essentially how a resonator can be modeled using a circulating field. This is how LIGO works as well. You have two mirrors, you drive the space between them using a laser, and then you start building up an optical field between the mirrors. So all these examples of kinds of resonances. And so here's another example, a drum. So you have a drum. Now the drum is a bit more difficult because when you think about drums, the way you typically model the drum is using a standing wave model. So the shape of the drum skin when you hit it, the fundamental vibration mode is called it's called the drum mode actually, and the shape is a Bessel function which has a maximum in the middle and zeros at the edges. That's what you'd expect. And here is so that's a little bit troubling that you've got this standing wave model. And here again is a cavity. So this is an empty cylindrical cavity in the TM010 mode, which is the interesting one for axions. And there you have an electric field which makes a standing wave pattern that looks just like the drum skin, right? And the magnetic field makes loops that circulate around. So that's there too. So how do you understand these resonances using circulating field models? Well, it turns out that you can think of a drum vibration as the sum of two propagating waves. One of them is propagating from the center of the drum skin towards the edge, and the other one's propagating from the edge towards the center. So those are the two things in yellow at the bottom. They have funny names. I've forgotten the names of those. I think they're called Hankel functions. You add them together and you get the motion of the drum skin. Okay, but the point is that you can take what's normally modeled with a standing wave model and model it in terms of a circulating field instead. And this is just to show you that the cavity detector and a feedback-driven circulating loop detector are not actually that different. So that's, I guess we'll skip this one. It's pretty, but it's hard to explain. I'll tell you what it is. It's basically the black lines are the displacement of the drum skin from the center to the outside. And the important thing is that the displacement at the outer radius goes to 0. And the blue and the red lines are the two Hankel functions that add together to give the black lines. But it's a little bit hard to read because it's not clear where the drum is. The center is where the amplitudes are a maximum, and the edge of the drum is where all the black lines come together. Okay, enough of that. So this is a sort of cartoon picture of how my cavity is replaced by my resonance circuit. So here's on the left is the cavity, and you've got currents flowing in the walls of the cavity, and you've got electric fields sloshing up and down inside. Now I peel the sides off the cavity, so I've just got the end plates. And so instead of having currents flowing in the walls of the cavity, my current flows down a wire. Now, because I've taken away the side walls, there's no longer a preferred frequency of oscillation associated with the electric fields. But I can still pass my currents through a filter. So that's what the triangular thing on the right is. And that filter then sets the mode frequency. So it's a new kind of resonator for looking for axions, which is controlled by an electronic circuit external to the cavity. And that's its first advantage. You don't need a tuning rod. So all that mechanical mess that you have to put in to tune the mode, that's all gone away. The second advantage is that there's no dependence of the frequency on the size of the electromagnetic structure. The frequency can be whatever the resonant frequency of your circuit is. So you can look for axions over a much wider range of masses with the same equipment. And so here's how it kind of works in sort of pseudo reality. you have your gap between your electrodes. Now it looks like a capacitor rather than a cavity. And then you amplify the signal from one of the electrodes, still in a very cold amplifier, very low noise amplifier. Then you have a resonant filter, and then you probably have some more amplification and an attenuator at low temperatures, and then you feed the signal back into the other plate of the capacitor. That's roughly how it works. Now, why would you want to replace a cavity with all this mess? Well, I've given you two reasons. Well, the third reason has to do with the fact that you can make more than one resonance, because your resonant detector doesn't have to have just one magic frequency. It can have as many as you can fit in your electronics. And my calculations indicate that you can have about 100 of these resonances in parallel. You can also have parallel sets of plates, so you can make a large volume by having the signal from in the feedback circuit drive multiple parallel plate capacitors in parallel, and that way you can fill a large volume. So all this is a very nice idea. So in practice, you know, this is getting even more realistic. So the first amplifier is a Josephson parametric amplifier, which is a very low noise amplifier, followed by a couple of Hempt amplifiers, which are slightly less low noise but cheaper. And then you have some room temperature amplifiers, and then the actual resonator is made out of a digital circuit, which is implemented on a device called a field programmable gate array that some of you might be familiar with. And then the output of that electronics goes through a cold attenuator and goes back into the cryostat. And inside the resonant electronics, it's actually even more complicated. You basically have a circuit which is driven into quadratures. So you have to digitize the signal from the last amplifier, mix it down to a lower frequency before you digitize it, because the base frequency of the Axion search is probably a few gigahertz, and you can't digitize that fast, at least not trivially. And then when you're done with your digital signal processing to make the resonance, you convert everything back to analog, and then you mix back up to the frequency that you are trying to make a resonance at, amplify, attenuate, and re-inject. So this is my resonance circuit actually running. The horizontal axis is frequency actually, but it's in funny units. It's in radians per sample. So good luck understanding that. But as you change the value of this parameter W, you can make the resonance sharper and sharper. And in fact, in our experiments to determine whether this worked, we've achieved quality factors of our cavity modes, or pseudo cavity modes, of order of a million. So that's not bad for a little electronic circuit running at room temperature. And this is just some more implementation stuff that shows you how it's done. The whole circuit is implemented on a simple FPGA. It's an Arctic 7 device. And on that chip, you have some VHDL code, which implements the filtering. And then you have a little processor core called a microblaze, which runs a program that we write in C, which allows us to communicate with the filter code to change the frequency of the resonance. So it's a nice example of digital circuitry doing fundamental physics, which is something that's happening more and more in science research. So I guess this is an old slide showing me generating some resonances at some very low frequencies here at sort of 10 kilohertz. I've forgotten this slide was in there, and showing some very, very high Qs that we could achieve at these low frequencies. And then finally, here's what happens after we decided it works, is we install the electronics. So the box, which is third from the bottom in the rack on the left, is our resonant electronics that we built here at Sheffield, myself and a student called Mitch Perry, who's my PhD student. And the woman who's working on this at ADMX in Seattle, that's Chelsea Bartram, and she essentially wired this electronics up. And on the right, you can see a little test cavity, which we adapted to test this idea. So obviously this isn't a cold cavity in this picture, it's a warm cavity. But since this picture was taken, the electronics has been connected to a cold cavity actually in the insert, and we're doing tests on that right now. Here is one thing when you build these experiments is you have to model them, and you model them using finite element modeling in one of various packages. A popular one is called ANSYS HFSS. And then another one that I'm using here is a tool called Cadence Clarity. So you basically produce a model of the cavity, and then you can simulate the electromagnetic modes in the cavity and how they couple to external drives. The reason I'm using a cavity here, by the way, is because when we're testing the early electronics, we want to restrict the bandwidth of the electromagnetic waves in the feedback loop. And a good way to do that is to use a cavity as part of the loop. So the cavity is providing a restricted frequency range environment to make it easier to diagnose the equipment when we're developing it. And here's a picture of a simulation output from Cadence Clarity showing the appearance of a TM010 mode at the frequency where we predicted it would be, which is somewhere between 2,550 megahertz or 2.55 gigahertz and 2.6 gigahertz. So this is early work on simulations by Mitch Perry, my student. So this is the test setup that we currently have at ADMX. The cavity is bottom left in gray. The signal, there's only 2 ports on this cavity. The cavity wasn't built for us, so we're doing our best with what we have. So what we want to do is study the spectrum of the cavity in the presence of the feedback loop with the electronics. So we're trying to show that the presence of the electronics can induce extra resonances in the cavity. And we've got some data that shows that that can be done. Here are some resonant modes. That there are 4 resonant modes, actually 5 resonant modes that were produced externally here using 5 different filters, which are all in the digital electronics. So this was done in January by Chelsea. This just shows that we can make the resonances and we can make the loop gain of order 1. And if you remember, that's the requirement for making a resonator. Okay. So more recently, we've been actually running this experiment in the cold cavity, in a small cavity on top of the main ADMX cavity called Sidecar, and its natural resonance is around 4.8 gigahertz, which is about twice the frequency of the little test can that you just saw. This is an induced resonance in the cavity. So what you're looking at is noise from the cavity through with the feedback loop present. And you can see that some of the curves are quite symmetric and have high amplitude. So that corresponds to the case when the phase shift around the feedback loop is in a multiple of 360 degrees. So that's the other part of the microstability criteria. The gain around the loop should be 1, and the phase shift should be a multiple of 2 pi or 360 degrees. And then we tried other phases, and we noticed that when you dephase the loop, you still see structure, but that structure develops asymmetry and the amplitude gets smaller. And that's actually very good news, because this is exactly how a cavity resonance behaves. When you have a piece of cable that's quite long between the cavity and the electronics, you see exactly the same effect for exactly the same reason. The cable introduces a phase shift. The quality factor of this resonance is about 1 million, which is about a factor of 100 bigger than the quality factor of the resonance caused by the walls of the cavity. So that's also very encouraging, because we can get very high Qs. Turns out it's harder to get low Qs, but that's a technical issue which we shall solve in the future. Okay, so maybe I've gone for about long enough now. I'm just going to summarize. So what we have here basically is a set of energy states that we can create in our cavity, because every resonance we create corresponds to a particular energy or particular axion mass. We can tune the spacing of the states, we can tune the lifetime of the states by varying the quality factor of the resonance. We can do all that dynamically by adjusting the filters in the digital circuit. The amplifier chain is in the gigahertz frequency range. We would expect that if we were to put the signal in the feedback loop onto an oscilloscope, we would see a fuzzy sine wave. And that fuzzy sine wave corresponds to a state which optical physicists call the Glauber state. So we should, with this apparatus, be able to directly observe with a fast oscilloscope time-domain Glauber-like states, which would be very interesting and indicate that we are truly doing quantum mechanics with this feedback circuit. We can drive this configuration with injected signals, electronic signals injected, classically particles, ions. We could make this apparatus interact basically with other physics. And the other thing is that the digital filters we've used are a small subset of a very large class of filters, which may be interesting for other things. So this slide's basically meant to show you that this is maybe an Axion detector, but it's an Axion detector which also has possible lots of other applications in other areas. So even if you don't like dark matter and you don't like axions, you might still like this kind of physics. So the summary is that ADMX in its current form with a cavity mode that's tuned and a tuned receiver is still taking data. It's still the world's most sensitive axion search. It's funded in the US under a scheme called Generation 2 Dark Matter Experiments. It's got a Generation 3 proposal in the pipeline. Hopefully it'll get funded again. This resonant feedback idea is sort of my baby, but I've got a group of people working on it now, and it could conceivably speed up the search rate by quite a lot. We could basically cover the entire ADMX search range in 40 days. As compared to 3 or 4 years with the current apparatus. And we do that because we have multiple resonances where they only have one. This idea could turn out not to work. There could be some reason why it fails, but at the moment we're still studying it, and we have this sort of sneaking suspicion it will work. And the same ideas are applicable to other hidden sector searches, and we are building and studying the prototypes at ADMX to explore this idea and really try to get it working. And there are probably applications of what I would call quantum limited resonant feedback beyond dark matter. I find these very interesting, and in my Sheffield lab I shall try and explore these further in the future. All right, well, you know what? That's the end of my talk, and I have been going for probably 45 minutes, so I'm going to escape talk and see if we're all still there.
Yeah, thank you very much for your wonderful presentation, sir.
I hope you liked it.
If you allow, yeah, if you allow, we can start discussion. We have got few questions in inbox, so if you allow, we can start.
That's fine.
I think our students have learned a lot of things about the dark matter axions. So we got few questions. So first, do neutrinos help us to detect axions?
Okay, so neutrinos are these very, very light, weakly interacting particles that are made in the decays of things like neutrons. And at one point, people thought neutrinos might be the dark matter, because we know they exist. That's their great advantage. We've detected them, right? These axions could be total nonsense, right? But neutrinos, we know they exist. The answer is they're not actually coupled to the axion really at all. They're a completely different sector of the theory. They were sort of ruled out as dark matter, and the reason is because we know that the universe is full of structure. We know there are galaxies, we know there are clusters, we can see all these things, and indeed we're part of the structure, right? In some sense, a great example of structure is this machine here, right? How the hell do you get that? So the reason you get that is because the universe was in a state where it could condense into structures. And neutrinos would rather have spoilt that, because neutrinos in the very early universe were hot, they had very high energy. And so if there are a lot of neutrinos in the early universe, they would have inhibited structure formation, and the universe would be a sort of homogeneous goo instead of full of all this beautiful structure, which it is today. So we don't think the neutrinos are the dark matter, and I'm sure the questioner maybe knew that. But the point is that you can't really couple neutrinos to axions. Axions have pretty small couplings. Well, okay, I'll modify that. There's a little sense in which you can. Remember that triangle I drew that had fermions in it, had electrons, I said, or maybe quarks? Well, it's possible that there are also neutrinos could form that loop as well. But they'd be what's called virtual particles or helper particles for the conversion of axions into photons. So their contribution just gets added into the contributions of all the other fermions. So it's a very passive role they play there. That's the extent of the role they can play, I think. I hope that answers it.
Yeah. So thank you, sir. We have another question. So how do we determine the quantum number of axions?
Well, okay, so the people who invented axions didn't just pick a number out of space and say, look, maybe this thing exists. They was a very specific mechanism. They were basically trying to design, you've heard of the Higgs boson. Now, what Higgs does, the Higgs is produced in what's called a spontaneous symmetry breaking mechanism, which is a mechanism where, you remember that wine bottle potential I drew that had a hump in the middle? Well, at very high energies, that hump doesn't matter, because if you look at the bottle from way above, it looks like a flat bottom, right? It's only when you get close you realize there's this hump. And so if you have a ball bearing rattling around in the bottle, if you cool the ball bearing at high temperatures, it doesn't care about the bump. It just rattles around everywhere. But as you cool it slowly, it realizes it needs less energy to be at the side in the pit than it does to be in the middle. So then it picks a direction. And picking a direction is called spontaneous symmetry breaking. And that technique of using spontaneous symmetry breaking to make physics do things that it doesn't otherwise want to do was basically started out with the people who invented the Higgs boson, because they were trying to unify electromagnetism and weak sector physics. And there was a spontaneous symmetry breaking mechanism that did that. But Peche and Quinn, who invented the spontaneous symmetry breaking mechanism that made axions, they were trying to force the CP violation out of the strong interactions. And so the axion that's produced, its properties match what they would need to be for the Peche-Quinn symmetry to correctly explain the behavior of quantum chromodynamics. So it's a sort of long chain of arguments that leads you to a particle that has very specific properties, which is a sort of byproduct of this mechanism called the Peche-Quinn mechanism. I know that's a big mouthful, and this is why I don't try to explain axions in detail in talks. It's because it's so complicated. But I think it's actually quite compelling. It's just the maths is ferocious. Well, I hope I answered that one okay. I can't hear you, Pretam. Your audience.
Thank you, sir. Yeah, we have another question. So, are dark matter created immediately after the Big Bang or later?
Okay, that's a really good question. Of course, everything's created after the Big Bang. The only question is how long after, right? I mean, if you believe it really is the Big Bang, there wasn't a hell of a lot before it. In fact, there wasn't even time. So the whole idea of before the Big Bang is an anathema. But sure, you can certainly ask when axions were created. Now, it turns out, roughly speaking, a few seconds after the Big Bang, roughly speaking. But the exact time of creation, just like the axion coupling to photons, depends on the mass. So if you make axions lighter, they're produced earlier. And if you make axions lighter, they're produced in greater abundance. All right, so if the axions are produced less than a fraction of a second after the Big Bang, then axion production collides with a part of the universe's history which we don't understand very well, called the inflationary epoch. In fact, to be honest, we don't even know if inflation is correct. The inflationary hypothesis was invented by Alan Guth. I actually know Alan, he was at MIT. And he's still waiting around for some experimental proof that it's right. And if it comes along, he'll go get his Nobel Prize, right? Because that's like a really, really big deal. But, you know, there he is at MIT waiting for somebody to prove that he was right. But at the moment, you know, you've got this inflationary epoch, but people don't really understand it. If axions were produced that early, by extension, we wouldn't really understand axion production either, because it's occurring in this environment where everything's crazy and we don't understand it. So the answer is a few seconds plus or minus, depending on the mass.
Yes, sir. So thank you for your wonderful presentation and discussion session, sir. So as we don't have any more questions, so we should conclude our discussion session, sir. The main aim of our
I just wanted to wish everybody well, because, you know, I read the papers. I know that in India and probably in Bangladesh too, there's a lot of problems with coronavirus. We've probably been very lucky because we've got over some of our problems. We may have more problems in the future, but I just wanted to wish everybody my best wishes and my sympathy in the bad situation that we're in right now.
Yeah, thank you, sir. So our aim also actually to motivate our student in this critical situation, as we have to stay at our house due to the COVID. So we cannot go to our campus and cannot continue our normal academic program. We can't go out due to the COVID, and this is the best way to communicate with our student. And I think we're trying. Yeah. And
we're in the same position. Our students are at home as well. I'm in the office because I live very, very close to my work. I can walk here in 10 minutes. So I come in, but I'm one of very few people who comes in. The department's basically deserted. I came in today because I wanted to have good bandwidth so that we didn't have problems with the internet.
Yeah, thank you.
So yeah, we're in the same position, and our students also are very frustrated by being stuck at home working on their laptops and whatever devices they have. A lot of them work on their phones. It's really hard. So everybody just needs to buckle down. It'll be over eventually. It's just really bad and difficult at the moment.
Yeah, this is very difficult situation while we are facing, and this is the new experience. So thanks, sir, for helping us in doing this. It's a great
it's my pleasure. Physics should be a worldwide pursuit. I really want to encourage students in Bangladesh. You should take an interest in these things. It's very, very good, wonderful for your brain. and wonderful for your country to learn these skills. And look, I just encourage you all. I think you're really fantastic students for sticking with a subject this hard under these circumstances.
Yeah, thank you, sir. Have
Right,
a
take
nice
care.
day, sir. And hopefully, we'll arrange another webinar with you after a few months later. And after the COVID, we'll definitely invite you for face-to-face session, sir.
Yeah, well,
That will
I'll
be
do it again sometime. Just get somebody else in. Everyone will get bored if it's just me.
yeah.
So get
Thank you,
somebody
sir.
else.